en fait. OK. Okay. I'm very sorry for those online. It took some time to make the diapo work, but now I think it's fine. Um, okay. So can you hear us online?
Yes.
Oui, c'est bon.
Ah,
Good.
non. Peut-être que si je fais, je crois que c'est ça. Okay.
Christian, can you talk just to see if you can hear?
Oui, yes, hello. Good morning, everybody. Can you hear me? Sound is good.
Shoei, can you hear us? We cannot hear you.
Can you hear me? I'm
Yeah.
Shohei. Good.
Okay, great. Oh, yeah. Sorry. Christian, maybe you can introduce. Christian, can you hear? Can you hear us?
Yes, so the sound is strange. It goes on and off.
Oh, okay. Ma- Perfect. Okay. So, first of all, thank you very much today. Thank you, particularly jury members. I know the timing of this presentation is a bit early, sorry, or a bit late for you, Shohei. I hope you had some nice coffee, hot chocolate, and croissant at the entrance. Yeah, let's start this defense, which gathers more than 3 years of work under the supervision of Alex Grandfort and Pierre Ablin. The title of the PhD, but also of the presentation, is Multi-View Learning from ICA to Causal Discovery. But first, I know that this title might seem a bit obscure, for, especially for those who are not familiar with machine learning. But let's explain it a little. There are some terms that need to be explained, and let's start with learning. What is learning? Learning is extracting useful information or structure from the data. To do that, a learning algorithm improves each time it gets a new observation. And there are two broad ways of learning. The first one is called supervised learning. So it is when we have examples where there is a correct answer, and this correct answer is known. So we try to predict these. For example, you could think of trying to predict if a subject has epilepsy or the Alzheimer's disease, or even classify their sleep stages. The second type of learning is unsupervised learning, where you only have the data itself and no known answers. You look for a structure. You want to discover something meaningful inside the data. For example, an unsupervised learning algorithm would reduce dimension or try to discover functional networks inside the brain. During the PhD, we mainly focused on neuroscience data. Specifically, we focused on magnetoencephalography, MEG, and its maybe more famous counterpart, EEG, which are two non-invasive techniques that measure the electrical and magnetic activity. So these two techniques contains dozens or even hundreds of sensors placed around the head, with each sensor producing one time series, and they record the tiny differences in electric potential or the magnetic fields generated by the brain. The output of such techniques looks like the time series you got on the next to the MEG device. By applying a learning algorithm to such time series, you can actually extract some useful information that would be very difficult to detect by you. Or you could also automate some processes. But these kinds of data are exactly the data we used throughout the PhD. But let's give an example of what an unsupervised learning algorithm can do with MEG and EEG. You have here such recordings, and you can spot on these signals some recurring patterns. They are caused by eye blinks in orange and heartbeats in blue. Since they are unrelated to brain activity, we would really like to remove them from the data. This is exactly one of the things that independent component analysis, or ICA, can do. ICA separates the data into independent components. It is able, for example, to estimate here the components responsible for the eye blinks in orange and components responsible for the heartbeats. And once you have isolated these components, you can remove them and reconstruct the data, which is much cleaner. So mathematically, I said that ICA tries to separate the data into independent components. And to do that, it models the observations, which are called X here, into a mixing matrix A multiplied by some underlying sources, by a vector S, all sources or the components. The goal when you have this model is to estimate the underlying sources S from the observations. To do that, one remarkable thing is that actually this is possible, or at least it's possible under some indeterminacies. And this brings us to the notion of identifiability. A model is said to be identifiable if different parameter values lead to different data distributions. So, in other words, if a model is identifiable, a perfect algorithm could, in principle, always recover the two parameters. In the example of ICA, we can notice one thing, and that is that if you permute the rows of the components, rows of S and the columns of A accordingly, and you end up with the exact same observation. Is the same if you change the scaling. So this shows that actually there are two unavoidable ambiguities in ICA: permutation and scaling. These cannot be resolved by the method. But actually, the good news is that these are actually the only ambiguities of this method. So in neuroscience experiments, we often have I mean, sometimes we don't have a single data set. We often have several related data sets, several related data sets that come from the same underlying system. For example, you can think of having the data from multiple subjects who performed the same task, such as hearing a sound or seeing a visual stimuli. The goal of multi-view is to combine these views and extract some shared information across them. Because if you have multiple data sets, then you can likely boost the signal-to-noise ratio and perform better estimation than if you had only one data set. But here's an example of what multi-view learning algorithm can do with the MEG data. Here we took the MEG recordings of 50 subjects who performed the same simple visual task that was they simply looked at checkerboard patterns. And previously I used the ICA algorithm to remove artifacts from data. Actually, this algorithm can also be used in other things, such as extracting some meaningful statistical sources. Here, this is exactly what we do. From the 50 subjects, we extract using an IC algorithm that is adapted to the multi-view setting. We extract some shared signals, shared sources that represent the brain's response right after the stimulus. But then, what are the challenges? What are the problems we tried to address the PhD? So the first problem is that, of course, looking for shared information is great, but people are different, and this individual variability is present in the data. So we should somehow account for this. Hence, you can see that in MEG data, sometimes we observe a kind of temporal variability across. Here, in the top row, for both rows, we took the MEG data of approximately 500 subjects who perform the same simple visual and auditory tasks. And in the top row, you can see the auditory data. So we extracted the main neural response for each subject. We grouped them by groups of age. So there are the younger subjects, the middle-aged ones, and the older subjects. You can see these neural responses on the right. What you can notice is that for the auditory task, there seems to be a dilation effect that appears here, as if the neural response of the older group started at the same time as for the younger group, but ended at different times. And for the visual task, the effect is different. It looks more like a time shift. Actually, the three groups have signals of approximately the same duration, but they begin at different times. So these kinds of temporal variabilities across subjects suggest that we should be cautious when we impose the idea that the idea of shared sources across subjects. Question, the problem is how can we model these delays and dilation? Multi-view ICA. The second challenge is about causal discovery. That is, discovering causal relationships, cause-to-effect relationships between variables in situations where we expect the different views to share approximately the same underlying causal system. Granted, there are already methods that do this, but they often rely on strong assumptions. So the question is, how could we relax these assumptions? We leverage something a bit new, like the cross-view correlations. Let's start with the first topic. So I already said that there exist extensions of ICA to the multi-view setting. It is the case, for instance, of group ICA, which concatenates the different views either along the time axis or the spatial. This is also the case of MV-ICA and shared ICA. But none of these methods actually account for the time variability. For example, the MV-ICA and shared ICA method the MV-ICA and shared ICA methods model the observations xi. So now you have one observation per view instead of only one observation in the single view ICA model. They model the observations xi as the product between a mixing matrix AI, specific to each view, and a vector S plus Ni. And inside this vector, you can see that there's a term, S, that doesn't depend on the view index. And this is important because it represents the underlying sources that are shared across people. But you can also see in this model that these shared sources S all depend on the same time index T, whereas we would like them to be, for example, evaluated at different times for different subjects. So this leads us to our first method, multi-view ICA with delays. The idea here is that we introduced delays in the model. And to do that, we added a parameter tau I, which represents delays either specific to each view or sources. So we added this parameter in the model. During the optimization, our goal was to estimate this parameter. To do that, we simply took the view-specific sources, so the sources in orange and blue here, and we try to align them across. And the second method we developed was an extension of the first one, because here the idea was to add dilations on top of delays. And to do that, we introduced another parameter, rho I, which represents the dilations. We introduced it in the model, and you now see that we can evaluate the sources at time rho I times t minus tau I, whereas before this simply represents the fact that we allow for each source and each we allow the time axis to move differently, to be shifted and dilated differently. So this is a bit more challenging, but only adding delays, because when you allow the time axis to be dilated, you end up with signals of different lengths, and you often it forces us to evaluate the signals outside of the sample grid. So we had to develop a better method than the previous. And to estimate all the parameters, the mixing matrices AI, the delays OI, and dilations OI, we actually wrote down the likelihood of the model, which can essentially be divided into three terms. So the first term, yeah, in blue, discourages the inverse mixing matrices from collapse. The second term in gray encourages the estimated sources to the chosen prior distribution. The last term in orange kind of adjusts the delays and dilations so that the view-specific sources SI align with the average sources. But the great thing about this approach is that we can actually show that in this model, the time parameters, the delays and the dilations, are identifiable, and so that means that if we have a perfect algorithm, we could in principle estimate. In the end, the method looks like the algorithm here. We first initialize the parameters, then we optimize them using the likelihood we saw before. And to help a bit with the optimization, we added a few regularization steps. For example, to recenter the parameter, or to smooth a bit. We also use automatic differentiation to facilitate derivatives and to improve the computations. Okay. But here are the results of these methods. Just 1 second. I don't know if I can remove. We have a small bar. Okay, sorry. That should be better. So here are the results of the two methods we developed. So multi-view ICA with delays and multi-view ICA with delays and dilations. Them in blue and orange. And we evaluated them in settings where delays and dilations were present in the data. And we varied a bit the number of views or subjects and the number of. So the first row evaluate how well we estimate the matrices AI. And the second row evaluates how well we estimate the delays and dilations. And in this figure, we can actually make a few observations. So the first one is that when delays and dilations are present, the classical methods like MIND-INRIA and group ICA fail to estimate the parameters. The second observation is that, of course, when adding dilations in top of delays, curve to the orange, of course, it improves the last observation is that if you look at the blue curves, well, in the two rows seem to be kind of correlated, suggesting that estimating delays and dilations and estimating mixing matrices kind of help each other. Of course, our goal was not to test the methods on synthetic data. We wanted to evaluate them on real data. To do that, we used the CAMCAN dataset, which contains more than 600 subjects who performed MEG experiments, including visual and auditory experiments. And from these data, we anticipated that we would retrieve the effect we saw before. That is, we sort of expected a positive correlation between age and dilation in the auditory task, and a positive correlation between age and delay in the visual task. And actually, this is exactly the result which suggests that we could be learning some meaningful time. This could as well improve the estimation of the underlying sources. So let's move to the second part of PhD. This part we worked a lot with Omar Sheab and Apo Ivarinen. So it is about causal discovery, but actually, what is causal discovery? Causal discovery aims to recover structure in the form of a causal graph. That means that you want to discover relationships between variables. When two variables are connected, you draw an edge between them, and you also draw an arrow to direction of that. Causal discovery often relies on strong assumptions about the graph, about the noise distribution. For instance, one of these assumptions is the fact that there are no unobserved confounders, meaning that sometimes we assume that there is no unobserved variable that influences. And causal discovery can also be used in many different domains, such as in economics or climate science. But here in the PhD, our goal was to infer relationships of cause to effect between brain regions. Well, I forgot to say, but when we conduct causal discovery in the multi-view setting, well, the idea is that we want to recover causal relationships that are consistent across the views. We expect the underlying causal structure to be shared across you. And this is what we want to recover. Okay, so I talked about causal structure, causal graphs. And in the PhD, we focused on one particular type of graphs, and that is directed acyclic graphs. These are graphs with directions, but importantly, no cycles. For example, here, each circle or each node could represent a brain region, and the weights you see on the arrows contain the strength of the causal influence from one brain region to the other. So this is an example of DAG. But mathematically, a DAG is often represented by its what we call its adjacency matrix. Build this matrix B, we consider an ordering of the graph, an ordering of the nodes of the graph, for example, the red, blue, purple, orange, and green. And we place in the matrix B the weights of the graph. In the sense that the entry Bij of the graph contains the influence of node J and node I. And there's a famous result about DAGs that says that the adjacency of matrix, a DAG can always be permuted to be lower triangular. So the intuition is simple. If you knew the permutation of the graph, so that each node only depends on the previous ones, then the adjacency matrix B becomes a lower triangular. But anyway, what matters the most is the matrix B and not its decomposition with the permutation P and the lower triangular matrix. So when you have multiple observations X that follow a DAG, and if you also assume no unobserved confounders, and if you also assume that the causal relationships are linear, then there is a very natural way to represent these relationships with a model. And this is what we call a structural equation model. The observations X can be written as Bx plus E, where E is a noise vector that contains independent components. This is a very useful way to model. For example, here, you can see with this model that the orange node in the graph, which is the root of the graph, no parents, it is only equal to its noise E4. Whereas in contrast, take the red node of the graph, with this decomposition, we observe that it depends on the blue and the orange nodes plus its noise E1. So on this model, the goal is to recover the matrix B, which contains both the graph structure and the causal weight, to recover B from the observations X. Actually, there are multiple algorithms that already do this. There are multiple algorithms that are able to estimate this B. For instance, this is the case of ICA lingam, direct lingam, and pairwise lingam. But these three algorithms are in the single view setting, and they rely on strong assumptions about the noise distributions, such as. So our goal is to extend them to the multi-view. Okay. So in the first method, ICA Lingam, the idea is very simple. So here, I forgot to say, but Lingam stands for linear non-Gaussian acyclic model. Here, the idea is very simple. You can take the structural equation model we saw before and reformulate it into an ICA model we also saw. And since we assumed the noise E to contain independent components, if we also assume that the entries of E follow a non-Gaussian distribution, then we have all the ingredients to use ICA, and we can estimate the matrix A, at least up to permutation. The good news is that the DAG structure of B actually allows us to get rid of these indeterminacies, permutation, and scale. So in the end, we obtain a method that can fully identify the matrix A, hence the matrix is right. But in practice, ICA Lingam sometimes struggles to estimate the permutation indeterminacy. So this is why a second method was developed. It is called direct Lingam. Yeah, again, the idea is very simple. In the graph you want to estimate, if you pick only two variables, for example, the blue one and the red one, and if you assume that that your goal is to estimate the direction of the influence, so does the blue causes the red or the red causes the blue? Well, in this situation, of course, we know that the ground truth is the image shown in the middle. We have that x2 is independent from E1, but the opposite is not true. E2 is not independent. We do this by following the arrows. So if you perform the two independence test, then you have a way to choosing which direction is the correct one. And if you can estimate one direction, one arrow, then it becomes possible to do it for the full graph. And once you have the full graph structure, it becomes also possible to easily estimate the causal weight, for example, using this. And the last method we build on is pairwise Lingam. And the idea here is very similar to what we just saw with direct Lingam. We only consider two variables. The only difference is that here we replace the test of independence by some evaluations of likelihoods. So the three methods we just saw, ICA Lingam, direct Lingam, and pairwise Lingam, are milestones of linear causal discovery in the causally sufficient case. They all share a disadvantage, a limitation, which is, as I said, that require the noises to be non-Gaussian, which is not always realistic in practice. So, that in the PhD, the goal was to develop multi-view methods. To do that, we consider the case where all the views, multiple views, share the same graph structure. as before, we model the observations of all views, the observations as a structural equation model, where so bi xi plus ei, where importantly, the noise vectors ei can be correlated across V. One thing you can notice in this model is that while the causal structure is the same across views, the causal weights are allowed to differ. This is simply represented by the fact that in the decomposition of the adjacency matrices, have a single permutation matrix P, where you can have multiple different here, once again, our goal is to estimate the matrices PI, contain the graph structure. So we started with the first of the three methods. Here we considered the structural equation model and reformulated it into an ICA model, a multi-view ICA. Once again, multi-view ICA allows us to estimate the mixing matrices AI. And the DAG structure allows us to identify this ambiguity. So we end up with a method that gives us, that can identify, that fully identify. That's great, because actually multi-view ICA since recently is shown to work on Gaussian noises. So we end up with a method that works even for Gaussian distributions. The only disadvantage of this method is that the noises EI all depend on a shared vector S, which might be unrealistic in practice. So we moved to the second method, that it would be better. Here, use the same procedure and again consider only two variables of the graph. But now, having multiple views, which is great, allows us to perform the tests on vectors, the independent tests on vectors across the views, instead of doing it only on scalars. And this actually allows us to get rid of the non-Gaussianity assumption. And yeah, so we replace independence test by correlation or test of uncorrelatedness. The method becomes quite simpler than. Okay, and the last method is pairwise lingam. So our multi-view extension of the pairwise lingam. And here the idea is very similar to the previous method. We start by only considering two nodes of the graph. And the only difference, the main difference, I mean, with the previous method is that here we replace the test of correlation by evaluations of likelihoods, in the sense that we compute the likelihoods of both directions and choose only the one that is maximized. So in the end, here is the summary of the last two methods, direct lingam and pairwise. What is really great about this method is that we can actually show that they can identify we can identify the matrices BI, which contain both the graph structure, and identify it under very mild assumptions. For example, we we do not need assumptions at all on the noise distribution. Really, or we can we don't need the assumptions about changes in causal mechanisms, which was the only thing we need here for the methods to is correlations across the views, some simple correlations across the views. So here are the results of our method. In blue, directly down. And in different scenarios where we varied the number of variables. And what we can see on figures is that pairwise limba and direct limba consistently perform the other. This is great. And we also tested other settings, such as when changing the noise distribution by including Gaussian and non-Gaussian distribution. And the results were similar. We also reported the time, the execution time of the method. That they are quite that they could be used in practice. Okay, but once again, the idea was not to use these methods on synthetic data. What we wanted was to use them on real data. And ultimately, our goal was to discover causal relationships between brain regions that were consistent across. So we started with MEG. For this experiment, we took the MEG power envelopes of almost 100 subjects who performed the same task. They were asked to press a button right after hearing a sound. And since this experiment involves the auditory regions and somatory centers, just on the small passes shown here in pink and blue, hemispheres of the. And what we observed when running our methods on these data was that we mainly get connections from one region of one hemisphere to the homologous, the similar region of the, which was kind of. Then we applied our method to another type of data, MRI data from 9 subjects who performed a task where they were presented pairs of words and they were asked whether the 2 words rhymed. Being our method, we obtained here we report the main causal connections. That is the ones that are the strongest and most consistent across. What we can see here that the flow mainly goes from the input, the left occipital region, then from the left occipital region to more decision-involved regions of the left hemisphere. Finally, from the left hemisphere to the is right, because exactly what we expected for this task. So, in the end, during this PhD, we mainly tried to address 2 things. The first one was extending multi-view ICA methods so that they account for time variabilities across subjects. know this variability to exist, to be present. Second part was about causal discovery, and doing causal discovery in a multi-view setting under much more, much weaker assumptions than. In conclusion, I would say that this PhD, this 3 years PhD, has introduced me to the world of scientific research. And it taught me how to code and how to write a paper. They also taught me that science takes time. Progress is often made by building on methods that were developed years or even decades before. But above all, I would say that this journey was the opportunity to meet wonderful people in the lab, make friends. That's rigorous, but also deeply human. Sure, I don't know if you can hear us, but you can start the questions.
Oh, okay. So then I'm interested in what kind of temporal variability remained unaddressed in time series, or more specifically in fMRI or MEG or brain activity time series beyond delays and dilations. I mean, any other major forms of temporal variability than delays and dilations.
Yeah. So yeah, of course, delays and dilations are simplifications of all the temporal variabilities that could happen in practice. Maybe a better way would be to use time warpings, more complex time warpings. Would be to use time warpings. So that's something that we started doing with Omar 1 year ago, but we stopped. But an idea could be, for example, to use piecewise linear time warping of the time axis. And by doing this, you would first you would end up with signals that have always the same length, because you can adjust the starting time and ending time of the signal. But you could also, in the experiments, the MEG experiments that we saw, where you have a stimulus onset, you could also divide the time axis into meaningful parts. For example, you could have a first segment during the baseline time, before the stimulus, and one segment just after the stimulus, and then one long-term segment. Yeah, so the answer is that, of course, we could do better than delays, dilations, for example, by using time warping.
Okay, so why did you focus on the two variability in your thesis?
Yeah, by simplicity, because it was the simplest thing to model. We even started only with delays, and then I did dilation.
Okay, thank you. Well, can I ask one more question, or
Yeah,
should I stop? Can
you can ask as many questions as you want.
Okay, thank you. Okay, so Well, you make some assumptions, and I'm interested in which assumptions can be tested from data and which cannot, and then you would use your background knowledge to defend those assumptions. So can you explain which one can be tested from data and which cannot, and how you defend that
Yeah.
those assumptions?
Yeah. So, we made a lot of assumptions for the two projects. For example, if we focus on the second project with multi-view causal discovery, one of the assumptions was to have a dense connectivity across matrices. I think that in the end, the assumptions are difficult to test in practice. The great thing, I mean, the main assumption of the multi-view that for each pair of variables, if you want to discover the direction of then you must have two views such that these views are correlated and the variables are correlated as well. So when you have a lot of views, intuitively, it is very likely that the assumption becomes MIND. It is very likely that there are only two views that fulfill this assumption. But I think it would be difficult to test it quickly. So I have no better answer than saying that for this particular assumption, for the second project, if we have a lot of views, then I think it makes sense to make. I think it's quite weak. The only problem would be if you know that the two variables have no reason to be correlated, and for this particular situation, I think that the one thing we could do would be to improve the method, include a step in the method, so that in the end you evaluate if an edge exists in the graph. That would be something you could do instead of testing if the assumption.
Okay, thank you. Okay, so okay. So well, basically, I like linear methods. The linear approximation would work in many cases, but depending on what I mean, depending on your research questions, I'm wondering if in some cases you essentially need nonlinear models. So are there any such cases that essentially you need nonlinearity in your model, or in most of the questions you could have then linear model could be enough good, or
Yeah. Of course, nonlinear extensions are often considered when we impose a linearity constraint. It could so multi-view nonlinear ICA exists, and multi-view nonlinear ICA exists too, but under maybe more under stronger assumptions than ICA. So I don't have the answer but I think that it would be very interesting. But I don't know how would the identifiability if the identifiability of the model would still hold if we nonlinear that would be really interesting, but
I'm interested in, I mean, did you feel that you need nonlinearity when you analyze fMRI data, or linear method, your linear method did work well for your purpose?
So the multi-view ICA extensions we developed were only used on MEG data. We didn't. On these data, it is complicated to say if I felt that we needed nonlinear extensions. I think the fact that we end up with delays and dilations that make sense could suggest that the linear transformations, but I don't know if it's maybe it would be worth trying.
Okay, thank you. Thank you for your clarification. I have no further questions. Thank you.
Is it my turn? Yes. Ambroise, can you hear me?
Yep, perfectly.
Okay. Well, thank you for the invitation to your PhD defense. I was very interested by the manuscript, the topic. Those who know me know I enjoy a lot ICA. I'm a passionate user of ICA. So your new developments are very interesting. Bring new directions. Also, the causality I found extremely interesting. So I have a few questions. The first thing that came to me is really the matter of concatenation in space and time. You are mentioning that quite briefly in your manuscript, but to me, the most natural way I would have seen it would be to concatenate across the space dimension. So consider as one big space and concatenate the time series one after the other. So why did not you consider that? What was the rationale? I'm not sure. I see that there are different kinds of variability you would have to cope with, but what is your reflection on that?
Yeah. So, first of all, I think we do not really concatenate along the time axis. Consider, of course, the time axis in the sense that we consider temporal ICA and not spatial ICA. So if the question is, could we apply these methods to spatial ICA rather than temporal ICA, then I think this is very interesting. And in principle, it would be very interesting if, for example, we would have data from multiple subjects. So spatial data, you have the voxels and the time, the timings. You perform multi-view spatial ICA on this data. In this situation, allowing the estimated sources to be delayed or shifted would mean in practice that we allow one region of the brain to be kind of shifted a little bit from one person to that would make a lot of sense. That would be interesting if we could run a multi-view ICA while allowing the estimated sources to be spatially a bit different from one. I think that one problem this, or at least the reason why I think that would be difficult to directly use our multi-view ICA extensions to this situation is the fact that when you use temporal data, you have a structure such that two time points are always next to each other. But when you have when you consider voxels in the brain, not sure whether two consecutive voxels are always next to each other in the brain. And if this relation doesn't hold, then it would be strange to run multi-view ICA with delays or with delays and dilations on this data. Yeah, so maybe if we want it to work, we would need a sort of a transformation from the 3D space of voxels to the 2D space of the observation matrix X that would keep the distance between voxels meaningful in the sense that they represent those in the brain. And if we are able to do this, then maybe we could run our method on a spatial and I think that this situation, the problem would be very interesting. Really,
Yeah.
yeah, maybe we would need another method that does not model delays, but takes into account the distance in the brain between the two voxels.
Yes. Yeah, I think the two dimensions are interesting to look at, definitely. And then you would be in the source space also, which would be interesting. Now, a related question is what happens if you have subjects that's a general problem in neuroscience, subjects that have different strategies, so that can have different activations in the same protocol, so that would be for more complex cognitive processes. Can you cope with different groups? Will this go to different components? How does this work?
So is the question about outlier subjects like
or groups you could have
or two groups of people who have different neural types of neural responses?
Exactly. Yeah.
Then so maybe one thing that would happen if we run our methods on such data would be that if we allow for example 10 sources, then we could I'm not sure, but we could maybe the algorithm could automatically maybe estimate 5 sources for the maybe more involved in the first group, and the next 5 sources more involved in the second group, and that would probably require a visual inspection, but the delays and dilations could be meaningful inside each of these groups. But
that you would have to identify a posteriori the groups and discard maybe the delays for the non-meaningful.
But maybe one drawback of doing this is that it would require increasing the number of sources. I think so, and you may have seen it, but one potential disadvantage, limitation of our method is that multi-view ICA with delays and dilations struggles a bit when the number of sources. It is very limited because probably because it is synthetic data. But still, I think that when we allow the sources to be delayed and dilation, delayed and dilated, becomes simple to make 2 sources. So in the situation where we have 2 groups, if we want to increase the number of sources, it could be possible, but we should maybe be
Another question, always related to the philosophy of group ICA. So I'm not used to group ICA, and I find it very interesting. One advantage I would see is that potentially you can unravel sources with low signal to noise ratio. The group effect could push forward activities, for example, deep activities that are very small at the sensor level, but then it's the group ICA that managed to see it. Now, I saw that you're initializing with a single view ICA. So potentially, can you lose things that are weak in each subject, but could be revealed by the group? I guess it's very difficult unless you would simulate it.
Yeah.
But can you anticipate whether you can discover low signal to noise activity?
That's a good question. I don't know. I know that in practice, the initialization step was useful, not necessary in the algorithm, but useful. This is what we observed. But it's possible that if we do not use this initialization step, we would maybe recover some sources that are very difficult to estimate. I don't know. It's a good question.
Yeah, you need simulations, I guess. Now, my last point is on the connectivity measures, directed connectivity, causality. So your yeah, slide 32, I think. Oh no, not 32. Sorry, it's I'm mixing up. Where you just show your graphs where you compare fMRI and MEG. Yeah. Yes. Um, I always find it very difficult to validate directionality in real data. It's a big so I don't have the answer. But here I found it a bit strange that you have from motor to auditory, whether you listen to something and then you respond. I would have expected the contrary, unless that's a feedback loop. So did you have a reflection on that? How do you know that direction is good or not?
Yeah, we also expected arrows from the auditory to the motor cortex. Yeah, the question of how can we validate the method is complicated. On this MEG data, I mainly relied on Alex. Explained me the fact that inner regions in the two hemispheres causally connected. But yeah, I admit that in this experiment, these arrows from the blue to the pink do not make sense. That suggests that the method is not perfect, and that among the top causal connections, some of them do not make.
Well, the connections make sense. Now the directions, it's always difficult to know which one is valid. So I hope you had some ideas on that. Maybe compare also different directionality measures. Yeah, it's tricky. So, but yeah.
I think the results make a lot more sense on the fMRI.
Okay.
I don't know about the MEG experiments. Maybe the connection between the pink regions, so the auditory and the somatosensory region, where two lights. So the algorithm maybe estimated the edge, but not the direction.
I think there's a lot of reflections in your manuscript on the properties of the noise. If I understand well, they are very important for you to discover directionality. Maybe you would need to check the noise assumptions. I don't know if there's a way a posteriori to verify whether your noise behaved the way you want it to be.
Maybe maybe the problem is not the noise assumption, because in this method, precisely we try to remove it, and we do not have
Okay.
restriction. Actually, I just think of maybe one explanation. The reason could be that for the method to work, we need the views to be correlated. And in this MEG experiment, the setup was that was about motor preparation. So we looked at signals before and after the stimulus, but also before the stimulus, and that was important.
Okay.
And in a multi-view setting, what makes the view, what can make the view correlated is the stimulus. So maybe, not sure, but maybe that in this experiment, the reason why it performs worse than on the fMRI experiment is this reason, the fact that we are looking at the data before the stimulus, so the views are less correlated than in the...
Okay. Well, thank you very much, and congratulations for the great work. Thanks a lot.
Can you hear me? Yes. Thank you, Mr. President. Thank you, actually, for having me today. It's a pleasure to know more about your work. Actually, I really liked your manuscript. I found it very comprehensive and didactic. I think also it was well structured. And also, I'm using ICA for years now, but I actually discovered many things, many aspects that perhaps I disregarded before. So thank you for that, because I could learn even by reading your manuscript. Actually, what I really liked also were the approaches that you're proposing that are beyond the single view aspect is the most common one. And I think it can be actually open new avenues in our research. And we have some questions for you for that afterwards. So for my question, I will start by quite technical questions, and then I will move to more conceptual one, okay? So don't be afraid. Okay. My first question would be related on the first study on the delays. Actually, it's a bit linked to what Christian asked you before. It is where you fixed your Tomax hyperparameter. I was wondering whether it could be also population, specific to population, because in your case, you're working with healthy participants. But let's imagine that you use both CAM-CAN dataset and the dataset relying on MEG, but this time with mild cognitive impairment participants. So what is your view about that? Should you apply a different Tomax for populations, or what would you do?
Yeah. So the answer is that the Tomax and similarly the Romax, so the maximum value, we set them by looking at other studies. So mainly the study which made us start this project and which showed us these dilations. In this study, we looked at the maximum delay and dilation observed on their data. So we took their values. So about the question for healthy participants. I think that that would really be possible, and that would be interesting to have different subjects. extend the maximum delays and variations and perform this on the parameters learned. One when do that would be that as we when we allow the shared sources delayed and to be dilated, that allows them to change a bit their shape, position. So if you consider your responses like this, you have two quite similar allow them to move a bit and to dilate. End up in the end with estimating two sources that overlap. So if you extend the maximum dilation and maximum delay, then you increase the potential this outcome, this probability becomes more. This could be a limitation, or at least if we want to perform such analysis and to could be possible and it would be very interesting, but maybe we should reduce the number of sources.
Yes, absolutely. Thank you. Then again, it was about hyperparameters for the second study. I really enjoy that you actually try to explore like a different ranges of value to see whether it or not it would affect your observations. In particular, like the way you regularized your approach and you select the initialization part. It is quite elegant and really fun, like it. And you said that your regularization scale, like lambda one, is quite broad and didn't affect so much your performance. But it was applied, if I remember correctly, in 3 sources and with a specific Tomax of, okay, we don't care about the number, but I was wondering whether such range of the lambda regularization scale would be affected by these values in terms of number of views, number of sources, etc.
Yeah, we have 2 hyperparameters lambda.
The small one, sorry. This lowercase one. I mean, the manuscript has a lowercase. But
lowercase lambda. Is it the so the 2 uppercase lambdas are about changing the scale of the time parameters compared to the unmixing method?
Yeah.
Is it the
yes,
one?
it is the case.
Okay. So maybe I mixed up notations.
Sorry.
So yeah, actually in practice we were impressed by this when you give more importance to the time parameters to this is probably because of the LBFGS algorithm. So I don't remember what was exactly your question, but
Just because I really like the fact that, okay, you have a quite broad range for this case that wouldn't be affect the performance, but I was wondering whether if you change the other parameters, whether it would affect such range you're considering.
I remember correctly, we tried increasing the number of little views. When we increased the range, which is indeed quite large. I think it's
yeah, 10 minus 7 to 10 3.
Yeah. So this range maybe moved a little bit, but as it is very large, I think I don't remember which value we picked for. we had, I think it doesn't really need fine tuning.
Then that's the third study. You didn't present it during the formal presentation, but you also did like a very nice robustness analysis with correlations across several runs, I don't know, 50 runs, something like that. I don't know if you have the picture of the correlation maps. If you have it in mind, perhaps.
I don't have them. Yeah. That's not really usual process.
In the meantime, I can ask my question, so no worries. Don't be stressed about that. No, I was just wondering because I really appreciate that you did this kind of running. I was wondering whether you could have like some explanation about variabilities in the correlation rates you obtain, because sometimes depending on the this one, you have some changes in the number of in the
Sorry,
correlation
it's
scores.
so.
Yeah, you have some changes from one run to another regarding this correlation score. And I was wondering whether you would have some explanation for that, whether it depends on the group of participants you're considering to run analysis, and perhaps you might have some subgroups behaving differently, perhaps a little bit linked to the Christian, what said before.
Yeah. So one thing I didn't say during the two methods, direct MIND-INRIA and pairwise, no hyperparameters, so they are deterministic, and used the same exact same in for this figure. So this is the figure B, where each entry correlation between one and produce this figure among the 100 subjects, 30 or 50 of them that we randomly picked. Indeed, the only source of difference was the subjects.
Why you have some variabilities? Okay, I'll go back to that afterwards, but very nice. Yes, I also had a question about the way you select the areas. So in MEG, if I remember correctly, what you did after the pre-processing step, you picked like 10 areas within the sensory-motor area and the auditory one, which is perfectly fine. It's not a problem. I just wondered whether you also tried by picking like, or either all the areas, but perhaps because you have many sources, it won't work, or just like 10 random areas to see whether or not you have changes in the observations based on that.
So we chose the APARC Sud constellation of the surface, and yeah, I don't know. So the multi-view causal discovery methods are not limited. But yeah, running them with a lot of parcels. Why we picked some. And it would be very interesting to randomly pick those for a specific task, as these are simple tasks. I think it would be very interesting, but I don't know how much information we would take if we picked the random. But
For the random case, it's just to validate that your hypotheses are good, is not like biased by the choice of the areas. Otherwise, I would perhaps prefer to have more areas just to see whether they have some overlaps with what you obtain with the fMRI, for instance. Because you don't have exactly the same areas involved in both cases. So perhaps having a bit more areas in MEG could make sense. And in particular, in your case, if I remember correctly, you applied a template to perform source reconstruction. So you don't have like the precise anatomy for each participant. Is why perhaps you're not as especially precise as you would like to.
Yeah, this is the average.
FS average, yeah. It's not a criticism, just a way to ensure that what you observe makes sense and not like biased by your choice of areas.
Yeah, that's totally fine. And I agree that it could be maybe scientifically and more regions. For example, we could focus on these 10 regions and add 10 randomly picked regions in the brain. If actually causal connections, we estimate causal connections. That makes sense. That would be a way to validate.
Okay, so let's move to more like broader questions. That is why now I can say that link with the correlation maps I mentioned before. I'm a bit biased because I'm working in BCI and we observe a lot of intersubject variabilities. And I was wondering whether we could use your approach to address cell variabilities by using some transfer learning approaches or foundation model to capture some invariants across participants. So I would like to ask you whether your approach could be applied to this kind of problems. We have many problems in BCI, by the way.
So I don't know in I don't know how to apply it to BCI or.
Don't bother about the real-time approach. I'm not mentioning like just, it's more about classification and you have different tasks performed by different participants. And you know that their neurophysiological signature may differ from one participant to another. So how we could size the opportunity of huge data sets we previously collected to infer the intention of the participant, the new participant who is coming to the BCI visit, for instance.
But so the question is, could we apply or use such kind of method? Maybe not with time, but with another type of.
Yes.
I don't know to which theory it should. Because this method does not use the fact that it only uses the fact that two sample patients that are closed one after the other. It could also be closed with time, with time points that are closed. And something close. I want to learning and use such an approach on other types of data without analysis. And as you have this type of structure, that two observations should be meaningful, that two observations. I don't know if I'm not sure that answers your question.
It's just because when I saw like the correlation maps with different subgroups participants, I was wondering whether you could capture like some subgroup invariants and based on that infer perhaps their own behavior.
Maybe we could do it afterwards.
Yeah. once you have like this map, you could perhaps apply this knowledge to participate. I'm just wondering, I mean, it's just an open question.
Yeah. Probably that once we have, so for this method, we end up with one causal graph and different. Once we have estimated these parameters, it may be possible. Then do other steps to find groups of participants that behave similarly. Yeah, totally. That seems.
Okay. My last question would be about open science, because you mentioned that before. I'm a bit in favor of that. Just a small comment just for you. In manuscript, I tried to look at your GitHub repo, but it seems that the links are obsolete. It's fine. Just
Okay.
pay attention on that. Just a minor comment. No worries. I just wonder whether what you develop would be perhaps integrated on specific toolboxes, such as, just taken as an example, MNE Python or other toolboxes.
Yeah. So for the ICA stuff, maybe I don't know. For the causal discovery, we talked a little bit about this. That would be great. I think we maybe have to just improve it. Once we will have a perfect clean code, the idea would be to include them in, for example, libraries. Causal learn, or I don't know if that would be. That's in discussion with Mark.
Okay. Thank you very much, and congratulations again.
Okay, thank you. So maybe it's my turn to ask questions. I have maybe a lot of questions, but I will ask only a few of them. So I enjoy a lot your manuscript and your presentation. It was very interesting to read it and to listen to you today. And so maybe I can ask a question at the first part before of your work, and maybe concern the two parts. How do you handle covariable in your analysis when you have a data sets, but addition to that you have some information concerning the individual, like the sex, like the age, like a lot of information that you do. It's not. I think. How do you handle this kind of information in your method? Because it's.
That's true that we do not use it.
I know that, but how could you? Because it's important to have this kind of flexibility to handle this kind of information in the model.
Including the age or the sex of the
Mm-hmm.
I don't know how we could do it is to include that. Whether we should include them.
Maybe in the BLOS, I did some additional term. I don't know. Which,
Could that would be. Oh yeah, maybe you're right. We could add the term, for example, for the delay and variations that would push the estimated delays and variations over expected values for it. Yeah, that could be. I don't know how much that would be cheating. I think empirically that could work. Regress, for example, simply regress. they do, we could also add this information. Encourage the towards the effect. I think that's totally feasible. That seems simple to do, but I don't know. Yeah, destroy individual variability, because that's true that we have that older subjects tend to have dilated neural responses. If we impose, if we push these parameters towards these old subjects with weak, that would be very interesting to do and test if. But then, if we do this, I don't know how we could evaluate the method, because what we used in the first part was this experiment where we expected the parameters to be correlated, both these parameters to be corrected. Then we cannot evaluate the method using this. That would be.
Thank you. Again, for the first part of the presentation, I have data set to analyze, but the data set I have to analyze is different, very different from your experiments, in the sense that the observation I have from each participant are observed in so it's longitudinal data like you, but the observations are very sparse and irregular from one patient to another. So I have patients that are observed maybe 4 or 5 times across the range, and from one patient to another, the points are very different. And I would like to ask you if it's possible to have this kind of data set in your setting to. You understand my question?
Yeah, I think so. So you mean that for example,
for instance, for your MEG data, you have one point, a lot of very dense observation, and the point are observed at the in a very precise grid from one patient to another. And so I would, and so it's not my configuration. Yeah.
So that could work, but I think that the main question in this situation is, does such data belong to the multi-view or the multi-domain setting? Because usually say that data are considered as multi-view. Same joint distribution.
Mm-hmm. So multi-view in my case.
Okay, multi-view. Then in multi-view, principle, but the other thing is that here we observe these delays because of the stimulus. I don't know in your data if they are like resting state data. Then in this situation, it might be difficult because I don't know if we would find. I don't know.
No, it's not. It's more. You have a patient who go to the hospital, and at the hospital they collect some biomarkers, not necessarily neuroimaging, but biomarkers. And so the patient comes several times at the hospital, and each time we have several biomarkers that are collected. And so this describes the longitudinal views of the biomarkers. So we have maybe only 4 points, and so. And from one patient to another, we have different, it's not exactly the same time points that are observed. So it's
yeah, that could work, but if you only have like
yeah, this is main.
not sure whether method like they can converge. I don't know how many time points you have. But
Not a lot of time points, but maybe a lot of observations. Maybe and maybe it can compensate. We have few time points per patients, but a lot of patients in our data set. Maybe 1 million, for instance.
when how many?
1 million, but a lot of.
Yeah, but I think that it would be a bit too much for the method to have this many patients. Although we didn't try such setting.
Mm.
Lot more like this. I would say that it could work, but
Okay, so maybe I can switch to the next part of your work. And so my first question is about the literature. There is a big literature on the subject of structural equation model. There is journal on that, and the name of the journal is Structural Equation Model, multidisciplinary journal. So there is a big literature and a lot of researcher on work on that. And I was very surprised that there is no citation on that on your report, on your manuscript, because they work on structural equation model, they work on likelihood, they work on how to infer the parameters, they work on not completely the question you have, and your contribution is totally okay. But I was surprised to see that there is no connection to the classical literature of structural equation model. So I would like to ask you why.
yeah. So I don't know which citation we use.
Bolen, yeah.
Well, yeah, and I don't know if
Yeah, so in the literature of structural equation model, they classically use the term of multi-group structural equation model. So it's not exactly the same vocabulary, but you have the same kind of questions.
yeah, maybe one thing that we started discussing recently with is and that is not included in the is yeah, the distinctions with other works on group multi-domains. Although I didn't really discussed recently. And main reason, I don't know if that, but the main reason is that the domain methods assume marginal distributions that you can. Multi-environment, I don't remember about multi-group, but multi-environments often are a subdomain of multi-domain. I don't know about multi-group. This is a fourth, there is a fourth definition. There is not multi-view, not multi-domain. Don't know a lot.
Okay. You should have a look of this literature, because there is a very huge literature, statistically oriented, but a very huge literature on that subject. So you could maybe pick up some ideas on that. And so in this literature also, I think it could be interesting to see structural equation model with latent variables, because I think in this kind of application, it could be interesting to introduce latent variable in your modelization. And I would like to know why, because I think you heard about structural equation modeling with latent variable. and why you don't you use this kind of framework to modelize your experiment?
Yeah. So there's a multi domain. We didn't use model for simplicity because the main measures the methods they are simple. I think to well in this scenario. Of course, adding an observed confounders.
Yes, but we are not talking about the same thing, I think. When you talk about confounder, it's okay, but I talk about really introduce latent variable in the model, not in terms of confounder, and in terms of if I have several, so I have a concept that is not possibility to observe. It's not possible to observe it, to measure it directly, but it's possible to measure this latent variable from observed variable, and characterize the concept from observed variable, and then introduce latent variables that are you have a set of observed variables that describe the latent variable of the concept. For instance, it's in your neural imaging data set, maybe you have region, but the region is characterized by the lot of variable, and the region is characterized by some few observed variable. And this is the modelization you did. You did, okay, it's not possible. My region is characterized by the set of observed variable. And so I want to introduce the fact that the set of variables that characterize my region is related and linked to a latent variable. You know this kind of...
I don't know how much we could extend our methods so that they account for.
And I think it's not so complicated because I read your manuscript and I think it's very easy to adapt what you did and introduce for introducing latent variable.
Okay. Well, I just don't see.
Because you don't know really the questions, but if you're interested by that, we can discuss after. Okay, so thank you. Maybe I have no. So I really appreciate the fact that you took the time to analyze the identifiability of the model, and it was very important to do that. So you did it almost perfectly, but I found some maybe there is more than one error, but I found one, and maybe I can.
With pleasure. I've still 1 month, I think.
Okay.
Break them.
Okay, so maybe it's okay for me. Maybe your supervisor want to ask question or give a... Yes, of course.
Thanks, Ambroise. So I don't really have any question. I just want to thank you for these 3 years. So we were off to... This has not been the smoothest PhD trajectory, to be fair, and that's partly on us because so when Ambroise started his PhD, he had 2 academic advisors, and 6 months after, he had 0 academic advisors. So that was pretty tough. I want to salute your contributions. So you've been able to demonstrate a broad knowledge in terms of optimization of statistics, neurosciences, and causality. And I think you displayed this very well in the defense. And that's really a broad number of topics to master. So that's yeah. Congratulations on that. Congratulations on the defense, and thanks a lot for these 3 years.
I won't stand up like Pierre. Yeah, so I say a few words too. So I guess, I mean, technically, I think the day you started your PhD, you already had 0 academic advisor because you had the 2 academic advisors at the beginning of your internship, and by the time you effectively started, you went to 0. So the path has definitely been interesting, ups and down. I think a PhD is usually ups and down, and I think you went through this. I'm really happy that Omar and Apo Ivarinen could jump in the last year of your PhD and play a big part of the supervision, and probably that allowed you to go to the end today. I hope you learn a few stuff that you learn about yourself. I think a big part of the PhD is since you don't expect people to tell you what to do, you have to find the energy in yourself. And so that tells you usually a lot about what you care about and what you want to do in life. Think about this and think of what you want to do next. I think you're still looking for it. I think you did what you had to do, including today with your manuscript and the presentation. Could answer all the questions from the jury and basically deliver what was expected to deliver for you today. So congratulations for bringing this work to an end and completing this, I'm sure, very brilliantly according to probably what the jury will conclude. Don't want to influence the jury though. All right, thank you very much.
It's time for deliberation. So will you stay here, or do we need to go outside, or what?
I think you can stay here, and we will move
Okay.
outside. Fine. For the last PhD. Or I mean, you could keep my computer and but I think you are the only one with Apo, which is counted as a guest. I don't know if you have to stay during the deliberation or not. Okay. Okay. So do you want me to let you my computer? Okay. But there's only Apo.
Should I join this breakout room?
Yeah, so I suppose I'm not officially part of any committee, so I should probably not say anything at all. Although maybe accidentally I'm at the same Zoom room.
Oh yeah, the
Non, pas du tout, ta gueule. Ah. Voilà, hop, hop, hop.